Today we're going to talk about graphing roses. So I've taken the liberty of already plugging in 0, pi over 6, pi fourths, pi thirds, pi halves, and so on into our chart in order to save some time. And I've also labeled everything that has a negative R value in blue, so then it's a little bit easier to see what's happening. And then I've plotted all the points on the graph. So what we see, R equals 5 cosine 2 theta. 5 comma 0 is our first point, and then I trace accordingly. So 5 halves comma pi sixths would be next. Then I get to 0 comma pi fourths. And then what happens is, notice I end up in these negative values. So then my pi thirds value is down here. My pi halves value, my 2 pi thirds value, and then I'm back to the pole at 3 pi fourths. Then I continue going. So 5 pi sixths, pi, 7 pi sixths, and 5 pi fourths. And notice that the structure of this is going in a loop, so it's a pretty smooth graph. I say smooth, and then I draw something that looks like a bunch of zigzags. And I did it again. I'm not going to do it over. But I continue to go, and then I get back to 2 pi where I started. So I end up with this flower-looking thing. And what do I notice about this? We call these roses. So what do I notice about 5 cosine 2 theta? I notice that there are 4 petals. The length of each petal is 5, which makes sense because I have 5 cosine 2 theta. And then it started at the polar axis, so it started over here and then traveled in this direction all the way around. So it ends up going in like these smooth curves all the way around. So, oops. So it looks something like that. So let's try another one. Negative 4 sine 4 theta. So I start at 0, and then I go to negative 2 pi thirds. So that means I'm actually going this way first. And then I'm back here. Now, one thing that I may notice is that this doesn't look like it makes much sense. Like, why would 2 pi or 2 root 3 be the end of what's happening? And so what I want to think about is, well, I know that 2 square root of 3 is about 3.5. But where is R maximized? So that's something that I have to think about, because R is not going to be maximized at 2 root 3. So I didn't actually plot any of my maximum values here on my chart. So that's going to be when the inside is equal to pi halves or 3 pi halves and whatever, because sine of pi halves is 1 and sine of 3 pi halves is negative 1. So if I want to figure out where this is maximized, I actually have to figure out what theta is. So 4 theta equals pi halves means that theta has to be pi eighths or pi over 8. So I have all of these values that I should probably plot on my graph. And so pi eighths, I'm going to have a maximum at 4, or negative 4, sorry. So I should be down here. 3 pi eighths would be somewhere up here. 5 pi eighths is down, so that's going to be down here. 7 pi eighths will be up here. 9 pi eighths, again, it's a negative, so I'm going to go to pi eighths. 11 pi eighths is going to be down here. 13 pi eighths is a negative, so it's up here, and then 17 pi eighths somewhere up here. So I need to have those points on my graph as the maximum values. So it's going to go like this, then through the blue point back here, then through the red point up to the black point and back. And so that takes me up to pi over 2. And then I continue this process. So this 2 pi thirds ends up going down here, and then to 5 pi sixths, 7 pi eighths, and back, up, down, up, down. So what I end up with is this rose that has what appears to be 8 petals. So I notice that there are 8 petals. The petals have length 4, which again makes sense because I have a multiplier of 4 in the front. And we started at the pole, and then the max values are at all of these pi over 8s. So I have max values at these pi over 8s. Okay, we're going to use this table of values again for r equals 6 sine 3 theta. So I have plotted these points already, just in the interest of saving us some time. So we're going to start at 0, 0, then pi sixths, comma 6. So I'm sweeping out this way. Pi fourths, then back for pi thirds, I'm at 0. Then down to pi halves, 6, or I'm sorry, that's pi halves is negative 6. Then by 2 pi thirds, I'm back to 0. 3 pi fourths, I'm up at 3 root 2, 5 pi sixths, I'm here, and then at pi, I get back to 0. Now what you notice is that 7 pi sixths, I'm at negative 6. Well, 7 pi sixths negative 6 would actually be the opposite direction, so I actually already hit that. And if you noticed when I plotted these points originally, all of these red points were also blue, and the blue points are also red. So these two actually match up. These two actually match up. These two actually match up, and so on. So what you see is that each of these things ends up being repeated when I do this, and so my graph only has to go a period of pi in order to go all the way around. So I end up with 3 petals, and then it shows up twice. So there are a bunch of repeated points. Again, it starts at the pole, and I have 1 petal on the negative y-axis is what it looks like. But 3 petals, the petal length was 6. Now we're going to graph r equals negative 7 cosine 5 theta. So we would start at 0, negative 7, or I'm sorry, negative 7, comma 0. We move in this direction. Then we end up over here, sweeping back down, and so on. So in the interest of me not trying to graph something that's really hard to graph, I'm going to end up just tracing it. So it looks something like this as we move all the way around. But what ends up happening, so you see, and then we finish over here. So my trajectory looks like this. And also, the same thing happens on this one that happened on the previous one. So this repeats here. This one repeats here. This one repeats here. This one repeats here, and so on. So I end up once again with a period of pi in a problem like this because everything just repeated. Whereas on the front side of this note sheet, I went all the way to 2 pi. I didn't have anything that overlapped. But on these problems, notice that I have all of these points that are overlapping with each other. So the red and the blue end up overlapping. So what does that mean for roses in general? It means that when I have an even number on the inside versus an odd number on the inside, there are some differences. So it looks like there's twice as many petals as the number on the inside when it's even, but the number on the inside is equal to the number of petals when it's odd. So that's something that we have to keep in mind. Also, notice that when n is even, we end up with a period that is 2 pi, but when n is odd, we end up with a period that's only half as long. So the period is pi because all the points repeat themselves. In both r equals a sine n theta and r equals a cosine n theta, we have a lot of similarities. So the length of the petals was always the multiplier in front. And then we had a couple different situations, but similarities in both cases. If n was even, we had 2n petals. So for example, in this case, 4 theta, 8 petals. That happened in all of these cases when n was even. The angle between the petals was pi over n. So that's something that we may not have noticed before. But notice that the angle between each of these petals is 90 degrees, or pi over 2 in this case. The angle between these petals is 45 degrees, because notice there's 8 equally spaced petals, and if I have 8 equally spaced petals, that's 45 degrees between each one, or pi over 4. So that's true in n equals even, n being even cases. When n is odd, we end up with the number of petals being n. So notice 3 theta, 3 petals, 9 theta, 9 petals. And then the angle between the petals was 2 pi over n. So if I look at this case, and I have 3 equally spaced petals, that would be 120 degrees, which is 2 pi over n, 2 pi over 3. And so we see that showing up all the time. Now the parts that are different based on sine and cosine. So if we have a cosine graph, the petals start on the axis. So notice 5 cosine and 9 theta. We have a petal starting on the polar axis. Cosine starting on the polar axis. Cosine starting on the polar axis. Cosine starting on the polar axis. Now notice this one starts at the negative polar axis because we had a negative. But the sine graphs, they don't start on the polar axis. They technically start on the pole. So when theta is 0, they're right on the pole. But your first petal starts at theta equals pi over 2n. And that happens whether it's even or odd. So, for example, in this one, we have 2 sine 3 theta. This starts at pi over 6. So 2 pi over 3 is between each petal, And pi over 6 is our start. Notice that's pi over 2n. Likewise here, this one starts at pi over 4, which is pi over 2 times n. And remember way back in the beginning, when we had this sine situation, the first pedal started at pi over 2 times 4, which was pi over 8. Remember, all of our maximizations were at the pi over 8s. So that's something that we see relatively frequently with the sine stuff. Last thing, symmetry. The cosine graphs are always symmetrical over the polar axis. So if you look at all of these, if you draw a line at the polar axis, you would be able to fold it over and it would match up perfectly. For the sines, they're symmetric over the pi over 2 axis. So if you draw a line on the y-axis, those would fold over and match up perfectly.